Our next speaker is Roger van Peski. The title is Hall-Littlewood Polynomials, Branching Graphs, and P-adic Random Matrices. Please.
All right, thank you very much. Let me just share my slides. Okay, great. So thank you for having me, and thank you to the organizers for putting on this great conference. I'd like to visit St. Petersburg in person, but for now I'm happy to address you all virtually. So today I'm going to be talking about, well, the objects in the title. And I should say that this is also based on a recent preprint, and so you can find more details there. Let me first start with a sort of historical outline of this kind of problem. So there's a research direction that's often referred to as the harmonic analysis of big groups. And this basically began with these results of Toma and Voiculescu in the 60s and 70s, where they classified the characters of the infinite symmetric group and the infinite unitary group, respectively. And there have been a lot of results in this direction. So I'll just mention a couple of newer ones. There was this classification of infinite Hermitian random matrices, which are conjugation invariant by unitaries. And most relevantly for us is a pretty recent result of Alexander Bufetov and Chu from 2016, classifying infinite p-adic random matrices, which are invariant under GL infinity ZP. Actually, they did something slightly more general, but we're going to think about this concrete case. So there was this sort of program of Vershik and Karov, where they gave new proofs of these results, such as the ones of Toma and Voiculescu, and sort of new directions of generalization by recasting them in terms of branching graphs defined from symmetric functions. And there's also been a lot of work in this direction by many, many people, and I'll just mention Borodin, Gorin, Okunkov, and Olshansky, but really many people have worked on this. So what I'm going to tell you today is a new result on a certain branching graph defined from symmetric functions, in this case, these Hall-Littlewood polynomials. And this result can sort of be translated into the setting of harmonic analysis to recover that result of Bufetov and Chu, and also a newer results by Asiotis regarding infinite p-adic random matrices, and sort of clarify the connections between these results and these branching graphs defined from symmetric functions. That's what I'm going to talk about today. Let's start with some definitions. So the Hall-Littlewood polynomials, the way I define them, they're actually Laurent polynomials. So these are symmetric Laurent polynomials in n variables, x1 through xn. They are indexed by integer signature, lambda. This is just a decreasing and weakly decreasing n tuple of integers. And these are symmetric under permuting the variables. They're given explicitly by this formula. Here, this is a normalizing constant you don't really need to worry about. And I'll just say that usually these are defined as polynomials. And if the signature has all of these lambda I non-negative, then it will be a polynomial, but we want to consider it where they can be negative, and then it's a Laurent polynomial. They have lots of nice properties, connections to various areas. One thing I'll just say is that if you set this extra parameter t to be 0, then they specialize to the classical Schur polynomials, which are given, for instance, by this.
Sorry, may I please interrupt you? I've probably missed it, but what's v lambda of t?
V lambda of t, it's an explicit normalization constant. It's just some polynomial in t,
okay,
and
okay.
I haven't written it down, so
okay,
you haven't missed it. That's on me. Yeah. It doesn't really matter for us. Do you want me to say more about it, or is that fine?
It's fine.
Okay. So both the Hall-Littlewood polynomials and the Schur polynomials, these are bases for the ring of symmetric Laurent polynomials in n variables. And this allows us to define what are known as the skew Hall-Littlewood polynomials. So these are now in terms of a pair of signatures which are of different length, in this case, n and k, and the difference between their length is the number of variables. So, okay, how are these defined? Well, if I have a Hall-Littlewood polynomial, p lambda, this is symmetric in all the variables. In particular, it's symmetric in the last k variables. Because the Hall-Littlewood polynomials form a basis, that means that it expands uniquely in symmetric polynomials. It expands uniquely in terms of Hall-Littlewood polynomials in the last k variables. And then it has some coefficients, which are some symmetric polynomial in the first n minus k variables. And so we just call those coefficients the skew Hall-Littlewood polynomials. Now, by just taking this formula here, dividing out by the left-hand side, and then substituting real numbers for the variables. In this case, we're taking t to be a real number between 0 and 1. You get a sum of some expression in terms of Hall-Littlewood polynomials, which sums to 1. And it's a fact that if t is a real number between 0 and 1, these summands are all going to be non-negative. And so this means that we have a probability measure on signatures of length n minus 1. Given any fixed lambda, we have a probability measure on these mu. So this is going to allow us to define.
Excuse me, Roger, it was not maybe just you said this, but it wasn't completely clear. A probability measure is on what?
The probability measure is on the set of signatures of length n minus 1.
For fixed n?
Yes.
Thank you very much. Perfect. Mm-hmm.
Yes, so for each lambda of length n, I have a probability measure on mu of length n minus 1.
Perfect. Thank you very much.
Is that clear?
Yeah, perfect. Yeah, thank you.
Okay, yeah, thank you for the question. Please feel free to jump in if anything's confusing. Okay, so I'm just going to call this expression ln n minus 1 lambda mu. And these are, by the previous slide, these are probabilities. And so I'm now going to consider a graded graph. So this graph has a vertex set, which is the set of all signatures of any length. And I'm going to view these vertices as arranged in layers. So there's length 1, length 2, length 3. And now what are the edges? So there are going to be edges between adjacent layers. And furthermore, this is going to be a weighted graph, and the weight on an edge between lambda and mu in an adjacent layer will be exactly this co-transition probability. So this is, again, a weighted, graded, infinite graph with edges between adjacent layers in this grading. And because these co-transition probabilities are probabilities, you have a natural Markov chain on this graph where if I'm at lambda, then I move down to mu with probability this. So it's a Markov chain that will always move down one rung in the graph. And because we have this Markov chain, if you have any probability measure on the vertices at level n, then you can just push this forward by the Markov map, and this will give you a probability measure on the vertices at level n minus 1. Then you can keep pushing that forward, and you get what's known as a coherent system of probability measures on the first n levels. Coherent just meaning that if you push the measure on one level forward, you get the measure on the next level.
So excuse me, Roger, again. So you took geometric series 1, t square, and so on for your variables. But in fact, it seems you could have taken any. So you don't seem to have used that it's geometric series.
Yes. So I haven't used that at all at this point.
Okay, perfect.
You're absolutely right. As long as these expressions are non-negative, you can define this branching graph. When we get to actually analyzing the coherent systems on the whole branching graph, we sort of need the facts that we've put in geometric series here, because then the Hall-Littlewood polynomials simplify and we're actually able to prove things. And this is sort of generally true of these branching graphs defined from symmetric functions, that you could define them. You could define quite general ones, but we're only able to actually prove things about ones where we make very nice choices of these variables that we substitute in. Does that make sense?
Perfect. Thank you very much. Mm-hmm.
Thanks for the question again. Okay, so now the question that we always like to answer in these Vershik-Karov style results is, what are the coherent systems of probability measures on with one probability measure on every level of the graph? So, and again, coherent just means that if I take the probability measure that's on the nth level and push it down by this Markov map, then I'll get the probability measure that's on the n-1st level. So first notice that, well, convex combinations of probability measures are themselves probability measures. And if I have two coherent systems, I can just take convex combinations at every layer, and that will give me a new coherent system. So really, to find all of these, we just need to find the extreme points, the indecomposable coherent systems. And I'll just make a historical remark here that you can say everything I've just said, but with sure polynomials instead of Hall-Littlewood, and with ones instead of a geometric progression in T. And these are related to the branching multiplicities of unitary groups. This graph is known as the Gelfand-Tsetlin graph, and finding all indecomposable coherent systems is exactly equivalent to classifying the characters of this infinite unitary group, this result of Voiculescu that I mentioned earlier. So now I can get to the main result of this talk. So let sig infinity be the set of infinite signatures. So these are just weakly decreasing infinite tuples of integers. Now take this parameter t again to be a real number between 0 and 1. And we want again to find the set of indecomposable coherent systems on this graph G. The result is that it's naturally in bijection with sig infinity. And furthermore, under this bijection, there's an explicit description of the coherent system corresponding to a given infinite signature mu. And this explicit description is, well, okay, for mu, I want to say what this coherent system is. So I just need to describe the measure, which I've called m mu n at the nth level. So I just have an explicit formula which tells you what is the mass associated to a signature lambda at the nth level. And it's given in terms of this product, which may look a bit daunting, but it turns out that it actually only has finitely many non-trivial terms, and it's not so bad. You can even write down a sampling algorithm where you flip some coins and do something that will sample these measures at the nth level. So they're really fairly concrete objects. And there is context for this sort of classification. So first, let me just say a little bit about the proof. It uses explicit formulas. So this is where I care about this geometric progression that was pointed out. It uses explicit formulas for these skew polynomials when the variables are in geometric progression. And these come from work of Borodin on the fused higher spin stochastic 6-vertex model. There are more general formulas there that can specialize to these. I'll also mention that there's this previous work of Gorin on the Q Gelfand-Tsetlin graph. This is analogous to our graph, except that the co-transition probabilities are defined in terms of Schur polynomials with variables in geometric progression. And he also found that the indecomposable coherent systems are parametrized by these infinite signatures. There's also some work of Cesar Cuenca on certain special cases of McDonald polynomials, which again finds the indecomposable coherent systems parametrized by sig infinity. Okay, so now I'm going to switch gears a little bit and talk about infinite p-adic matrices and how that relates to any of what I just said. So, okay, we have the p-adic integers, ZP, we have these groups GLN ZP. They include into one another by just taking an element of GLN ZP and then mapping it to the matrix where I've just padded it with a 1 and then a row of zeros and a column of zeros. Now you can define this group GL infinity ZP as the direct limit of this chain of groups here. And you can also view this sort of more concretely as the group of infinite matrices over ZP, which look like the identity outside of a finite corner. So in other words, matrices such that there exists an n for which outside an n by n top left corner, they're equal to the identity matrix, and then inside that corner, they're given by something in GLN. And you can convince yourself that even though in general you don't know how to multiply infinite matrices, you do know how to multiply these and they form a group. And so the question then, the natural question here is, what are the indecomposable probability measures on infinite matrices over the p-adic field QP, which are invariant under left and right multiplication by any element of GL infinity ZP? And this is the question that was answered by this result of Buffetov and Chu. So they found that this set of probability measures is naturally in bijection with sig infinity bar, which is just infinite signatures where now the entries, they're still weakly decreasing, but they are not necessarily integers. They can either be an integer or they can be equal to minus infinity, where you take, in this weakly decreasing, you take minus infinity to be less than any integer. So it's essentially the same set. And so this might give a hint that these results are related. Let me just also mention that in their paper, they actually gave an explicit parameterization as well of what the measure is corresponding to a given element of sig infinity bar. And these random matrices are sums of matrices with IID entries distributed by the additive Haar measure on ZP, and these rank 1 non-symmetric Wishart type matrices, these are rank 1 matrices that you get by multiplying two vectors which have IID additive Haar entries on ZP. So to get to recovering this result, I'm going to need to talk a little bit about finite matrices. So there's this result which is analogous to singular value decomposition. It's often referred to as Smith normal form, which says, suppose that I have let's say an n by n plus k matrix over QP, then there always exist elements of GLN ZP and GLN plus k ZP, and a unique extended signature. So this again just means that I allow some parts to be minus infinity, such that when I multiply A on the left and right by U and V, I get a diagonal matrix with powers of P on the diagonal. And so these powers of P, or rather the exponents in the powers, I'm going to refer to these as the singular numbers of the matrix A. And it's true that the indecomposable probability measures on rectangular matrices, let's say n by n plus k, are given by taking such a diagonal matrix and then multiplying on the left and right by Haar distributed elements of GLN ZP and GLN plus K ZP. These are sometimes referred to as orbital measures. And the last thing that we need to recover this result of Buffetov and Chu is the following result, which says, okay, let's suppose that I have n less than or equal to m. So I have this in general rectangular matrix over QP. It's random and it's from this unique bi-invariant distribution, which has fixed singular numbers lambda. So this again is this one that I got by multiplying on the left and right by Haar matrices. So now I take this matrix and I remove the bottom row. So I take the top n-1 by m submatrix. This will have some singular numbers. They're in general going to be random, and their distribution is described by the probability that the singular numbers of A prime are equal to a given mu, a signature of length n-1. And this probability is exactly the formula that we saw before in terms of Hall-Littlewood polynomials, which we defined to be the co-transition probabilities of this branching graph. Here, you take this parameter t to be 1 over p, depends on p. And so this relates this operation of removing rows of a matrix to the co-transition probabilities that we saw earlier in this branching graph. And so I can now just, yes?
Excuse me, how do you prove this?
So the way that I proved it, this was actually proved in an earlier work for a separate purpose, and then just happened to be applicable here. So it's been known for a while since McDonald's book, for instance, that the multiplicative structure constants of Hall-Littlewood polynomials are the same as, up to some scaling, as the Hall algebra. They describe the Hecke algebra of the pair GLN-QP, GLN-ZP. And so this sort of translated to probability language, this means that products of random p-adic matrices are described by Hall-Littlewood polynomials in some sense. And now if you take one of those random matrices to be a projection matrix, then it's just cutting a row off the other. Then when you multiply the two, you're just cutting a row off the other one. And then if you sort of take appropriate limits on the Hall-Littlewood side, you will get this formula.
So here you only use invariance, no other assumption.
Only using
for any invariant measure, So
I mean, here I'm taking an invariant measure with fixed singular numbers. So this is any
orbital measure. Yes, any orbital measure. Yes.
Yes,
okay,
that's the only thing that I use.
So it's explicit, it's explicit formula for co-transition probabilities for orbital measure.
Yes, it's completely explicit.
Right. Okay, perfect. Thank you. Excuse me. Yes.
Yeah, you're welcome. And I'll also just say this, everything I've said works for any non-Archimedean local field with finite residue field. And this is because it's all derived from this result. And this is derived from McDonald's results on the Hecke algebras. And you know that the Hecke algebras are the same for any of these fields. So it's sort of, it all comes from there. So, okay, let me just say what the idea of the proof is. So if I have a measure on infinite matrices, this gives me a coherent system of measures on all of the finite submatrices. Where coherent, I just mean, I could take a submatrix and then take a smaller submatrix, and these measures have to be coherent. Furthermore, I know that the measures on non-singular finite matrices over QP correspond to measures on signatures. And I also know that passing to smaller submatrices gives me the co-transition probabilities of this branching graph. And so this, sort of hand wavily, there are some details here, but I hope this convinces you that you can just take results on this branching graph and kind of move them over to this random matrix setting. And that is how it works in the end. So I'm almost out of time. So let me just, in fact, I basically am out of time. So I'll just say, there are some results of Asiotis and the decomposition of these so-called p-adic qua measures. In these results, Hall-Littlewood polynomials sort of appeared mysteriously, but we're now actually able to give new proofs of these where the Hall-Littlewood polynomials appear very naturally and sort of explain why that is. And that's all I have to say. So thank you very much for your attention, for all these great questions. And thank you.
Thank you very much, Roger. I think a round of applause. And if anyone has any questions, please go ahead.
So let me ask one more question, actually, excuse me. Just you mentioned that the formulas you write are similar in spirit to formulas that occur in the higher spin 6-vertex model. So if I understood you correctly, it is just that the same formulas appear in two problems. But is it possible? Yes, exactly. Is it possible to see p-adic matrices somehow? Is it possible to see conceptual connection between p-adic matrices and particle systems? I don't know if this question makes sense.
Yeah, no, I understand. I understand the question. I'm just thinking how I can give a reasonable answer to it. So, I mean, I think the short answer is that we don't really understand this yet, at least. So these, I can say a bit more about these formulas. So it's been known for a while, since some work of Kirillov, how to write explicit formulas for these Hall-Littlewood polynomials when you have an infinite geometric progression in T. And these are often referred to as the modified, in this case, skew modified Hall-Littlewood polynomials. Really, the new input here is that you can get some sort of formula for a finite geometric progression. And I don't know how to see p-adic matrices appearing in these fused higher spin stochastic 6-vertex models. I mean, there's.
But excuse me, it's also finite formula that you need for proof of classification, right? You could not prove classification just with infinite formulas.
Yes, exactly. And that's why I mentioned this here. This is a very important ingredient, and this is sort of.
So you need this finite formula, and
yes,
this
you absolutely need it.
And this finite formula is just, so this is very, in fact, I should say it was not immediate to me from your preprint. Maybe I was not attentive enough. It was not immediate to me that this just co-transition probability, just in like in paper of Vershik in 1980, this just co-transition probability is precisely this polynomial. So it's just identity, in fact, as you said yourself.
Is precisely, you mean? So
your theorem from 2020.
Oh, yes.
No,
yeah,
different slide.
It is precisely that.
No, yes, exactly. This co-transition probability is just this polynomial. So there should be some connection, but this polynomial, so I think there should be some connection. It's just not possible that there not be connection. Well, it's much easier to say than to prove, of course. Right.
Yeah, I mean, it's still not clear to me, though, that there should be a precise connection, because the vertex model side makes sense for any, at least for any t between 0 and 1, and the p-adic random matrix side makes a sense only when t is 1 over a power of a prime.
So maybe there are some additional symmetries in this situation, for example.
Yeah. I mean, it's an interesting question. I don't see any way that we're close to an answer to it, at least given what I know. But I agree that it would be very cool if you could make some more conceptual connection and not just sort of port the formulas over.